In this video, we shall discuss on time series. You will learn all you need to know about time series. First, we'll start with the definition. Definition: for more on this topic, you need to subscribe to this channel. So the time series as a stochastic process is an ordered sequence of value. The time series is a collection of observations made sequentially in time. So time is very useful in time series, and as a stochastic process, it's an ordered sequence of observation. Yes, we also define the time series to be a collection of observation made sequentially in time. And sometimes we denote the time series to be xt, which is the value of the observation. That is for that. Now, the ordering is usually in time. The ordering is usually in time. Now, the time series occur in variety of fields. Variety of fields. Fields for time series. The time series occurs in varieties of fields. For example, we can find the time series in agriculture. We can find time series in business and economy, business and economy. We can also find time series in engineering, we can find time series in geophysics, we can find time series in medical science, we can find time series in medical sciences. Okay, 5. Medical sciences. 6. We can find time series in metrology. Metrology. 7. We can find time series in quality control. Quality control. We can also find time series in social sciences. Social sciences. So these are the areas or the fields where we can find time series. We can find it in agriculture, metrology, business and economy, engineering, quality control, geophysics, social sciences, medical sciences. Now, objectives of time series analysis. Objectives. Objectives of time series analysis. So what are the objectives? 1, we'll have the description. 2, we have the explanatory or explanation. 3, we have the forecasting. Forecasting or prediction. And 4, we also have control. So these are the areas where these are the objectives of time series analysis. When we talk about time series analysis, these are simply the objectives. These are simply the objectives. So a simpler, more useful way of describing a stochastic process is to give the moment of the process. Is to give the moment of the process. Now, the first and second moments are the mean. I mean, the first and second moments of time series analysis. A much more easier way of describing the time series is, like we have just said, is to give the moment of the process. To give the moment of the process. Now, we say the first and second moments of time series. Now, we have to put down the first and second moments of time series. One, we have the mean. The mean, which is also denoted as this, we write it as this, is equal to the expected value of xt, which is the value of time series. Also, we have the variance. We have the variance. The variance, which is denoted as this, can be written as the variance of xt. And this is also equal to, so we'll move over to this other side of the board to finish up that. We have to clean this side. For more on this topic, you need to subscribe to this channel. So we can now write the variance properly. The variance, we can complete it as the variance of xt is equal to the expected value of xt minus mu t all squared. So that's the variance. So the variance for the first and second moments of the time series can be written as this. Or we have again the covariance. The covariance, which we can denote as R into T1, T2. We can write it to be R T1, T2 to be equal to, now we can write the covariance of xt1, xt2, which is also equal to the expected value of xt minus mu t1 multiplied by xt2 minus mu t2. So this becomes our covariance. And the fourth one, this becomes our covariance. That means the first and second moment of a time series. Because before you can describe a time series, you must first describe the process or the moments of the process as we talked about before. Now, the fourth item we have is the correlation. The correlation function for the fourth one. So the correlation function can be denoted as the covariance of T1, T2 between between X T1 and X T2, and is defined as our correlation of T1 T2 is equal to the covariance. I'll write it out properly this other side. The covariance of xt1 xt2 divided by the square root of the variance of xt multiplied by the variance of xt2, the variance of xt1 and the variance of xt2, which also can be written as r t1 t2 all over the square root of sigma squared 1 t1 multiplied by sigma squared 2 t2. So I'll have to write this out properly. I'll write it out properly. To move over to this other side of the board to do that. So move over to this side to write the fourth item. Oh. For more on this topic, you need to subscribe to this channel. So this is just the peripheral of what we are to discuss. Like we have said, a simpler, more useful way of describing a stochastic process, which is a time series, is to give the moments of the process. So we have our correlation to be T1, T2. We are writing it out properly to be the covariance of xt1, xt2 all over the square root of the variance of xt1 multiplied by the variance of xt2, which is also equal to r t1 t2 all over sigma squared 1 t1 multiplied by sigma squared 2 t2. So this is simply the first and second moment of the time series. So this is how we can describe the time series. The next thing we are to go into is stationarity, but we'll discuss the autocovariance and the autocorrelation function. We'll discuss the autocovariance and the autocorrelation function. For more on this topic, you need to subscribe to this channel. In this video, we shall discuss on the autocovariance and autocorrelation function of a time series. Now, the autocovariance and autocorrelation function can be denoted as the autocovariance can be denoted as RK, while the autocorrelation can be denoted as PK. Now, for we to analyze this properly, we need to check their properties. We first state their properties. After stating their properties, we still have to prove these properties if they are correct. One, the first property we have is we say the autocovariance is equal to the variance of our time series, and the autocovariance is equal to the variance of our time series, and this implies that our autocovariance is equal to 1. This is the first property. The second property, we have our autocovariance RK is equal to R minus K, which also implies that PK is equal to P negative K. You can call it like that. Also, the third property we have for the autocovariance and the autocorrelation function, we have the third property to be RK is less than or equal to R0, which implies PK to be less than or equal to 1 for all K. So this is the property for the autocovariance and autocorrelation function. The first thing we need to do is to prove this function one by one. So we come here, we write proof 1. The first one on our list states that R0 is equal to 1. And by definition, RK is equal to the covariance of xt and xt plus k. So we can say for k to be equal to 0, we'll have R0 to be equal to the covariance of xt plus k, which is equal to the variance of xt. Also, we can note that we say given the variance of xt to be equal to 1, we have R naught to be equal to 1. That is R naught, which is our covariance, to be equal to 1. So this is simple. Also, we can also remove this xt plus k. So if we have this, since our variance is also equal to xt, since our variance can be written as this and is equal to this, and our variance is also equal to 1, at k equal to 0. So we can have that. So if k is equal to 0, it implies that R naught is equal to the covariance of xt, which is equal to the variance of xt, and the variance of xt is equal to 1, since k is equal to 0. So if we input k is equal to 0, this turns to 0 automatically, so we can have this as this. We can have this as simple as ABCD. So this ends our proof, but this is where k comes in. We have xt. So that's the proof for the first one. For the second one, RK is equal to R negative k. We can do it here. For more on this topic, you need to subscribe to this channel. Proof for the second one, we are given RK to be equal to R negative k. So this is what you have to prove. So from stationarity, the covariance depends only on log k. From stationarity, covariance depends only on log k. So since it depends only on log k, we can have our RK to be equal to, let's delete this part. Thereby having this in mind too, we'll delete this. So our RK can give us covariance of xt plus k. Also, R negative k is equal to the covariance of, this can move over to this side. So we can write it as then xt minus k. So it then means that if this is equal to this, it then means that we can say both the covariance of xt and xt minus k is equal to the covariance of xt minus k and xt. Of course, we say let s is equal to t minus k. If s is equal to t minus k, then the covariance of x and x plus k, we can write it as this. Thus, we can move over to this other side of the board. Thus, if this is true, if what I've written here is true, then we can write thus RK, which is our covariance function, is equal to R minus K. So the next one we go into is R number 3. So prove our number three. That number three, if you could remember, we are asked to prove how k is less than or equal to 1. From Cauchy-Schwarz inequality, from Cauchy-Schwarz from Cauchy-Schwarz inequality, we can remove this. For more on this topic, you need to subscribe to this channel. For Cauchy-Schwarz inequality, the covariance of xt plus k is equal to, okay, since it's bounded, is less than or equal to the variance of xt multiplied by the variance of xt plus k. So we say, but the variance of xt plus k is equal to the variance of st and is equal to 1 for stationarity. Is equal to 1 stationarity. Then we can simply write first to complete our proof or to show. We can simply write R, which is our covariance, is less than or equal to the square root of, since this is 1, we have 1 times 1. So we have 1 multiplied by 1, which is equal to 1. So we have succeeded to say therefore RK is less than or equal to 1. So we have succeeded in proving the properties of autocorrelation and autocovariance function of a time series. For more on this topic, you need to subscribe to this channel to get more on time series analysis. In this video, we are to discuss models for time series. So we are talking about the different types of models in time series: the autoregressive model, the moving average model, and the mixed autoregressive moving average model. First, we'll start with the autoregressive model. Autoregressive. So, the autoregressive model, denoted as A R of order P, this of order P, this is how it is denoted, is defined as, now we'll write the model, xt, which is pi 0 plus summation of I ranging from 1 to p, pi I xt minus p plus et. So this is the model for the autoregressive. This is the autoregressive model for time series. Now, this model we have here we can write out the general form for this model. We'll also write it out. Well, after writing it out, we'll also define the parameter. Now, the general form of this model can be written as xt phi 1 x t minus 1 plus phi 2 x t minus 2 plus then continues plus phi I x t minus p plus p. So we continue this way. This I, we can still write p here because this I ranging from 1 to p. So we can still write 5p here if you wish. So this is the general form of the model. Now, what are these parameters that are here? The xt is the time series value. This phi we see here, that is say phi 1, phi 2 to phi I. We call it parameter coefficient. They are the parameter coefficients. Also, we have our error term. The ET is known as the white noise. The white noise process, or you can call it error term. There's a white noise process, or you can call it the error term. So this is the autoregressive model. This is the general form. I've also defined the parameters. The parameters we have here, and these are xt. The xt is the time series values. Now, to take just some little example. For example, if you have also regressive model of order 2, autoregressive of order 2. This is the model. Autoregressive model of order 2. We can write it as xt to be equal to phi 1 x t minus 1 plus phi 2 x t minus 2 plus p. Also, we can also write our autoregressive model of order 3 model. We write it as xt to be equal to phi 1 xt minus 1 plus phi 2 xt minus 2 plus phi 3 xt minus 3 plus our error term p2. So this is how we can compute the autoregressive model of order P. The next thing to do is for we to write the other model. So we go for the moving average model. The moving average model. That one is of order Q, the moving average model. We move over to this side of the board to do that. For more on this topic, you need to subscribe to this channel. The moving average model is denoted as MA of order Q and is as defined as xt to be equal to mu plus summation of j to be equal to 1 raised to the power of q, sorry, to q ranges from j equal to 1 to q, then theta j or theta q, because j ranges from 1 to q. Then we have x t minus q plus our error term So this is the model. This is the model for the moving average. This is the moving average model. Let me write it out properly. The moving average of order Q model. So it's defined as this. Now, we can also write the general form. We can write the general form of this model. So we say general form. We can write the general form. More on this topic, you need to subscribe to this channel. So our general form will give us xt to be equal to, now we have, this is our mean. If you wish, you can include it. It is our mean. If you wish, you can include it. So we have mu plus theta 1 x t minus 1 plus theta 2 x t minus 2 plus theta q x t minus q plus et. So this is the general form. Now, all we need to do is just to define the parameters we need. We define the parameters. How do we define the parameters? We move over to the other side of the ball to define the parameters. For more on this topic, you need to subscribe to this channel. So defining the parameters, we have our xt. Xt is the time series values. So we can also write phi 1, phi 2, so phi j or phi q are the parameter coefficients they are the parameter coefficients. T is the white noise. Process or error term. White noise process or error term. So these are the things we need to know about this. For example, we might be asked to write the model for MA, moving average model of order 2. This two means order, the order, moving average model of order 2. So what do we do? The moving average model of order 2 can be written, we can borrow a leaf from this, can be written as this. So we have here, say theta 1 x t minus 1 plus theta 2 x t minus 2 plus the mean plus, now we can write theta q x t minus q plus et. So this is how we can write the MA of order 2. Also, we can be asked to write MA of order 3. That means the moving average model of order 3. Moving average model of order 3. We can write it as xt to be equal to, this mean can also come first. The mean, we can also come first. Yeah, so we have mu plus theta 1 x t minus 1 plus theta 2 x t minus 2 plus theta 3 x t minus 3 plus, we continue like this, plus, we come here, we write q x t minus q plus et. So if you are asked to write the moving average model of order 3, this is how we can compute that. That's how we can write it. That is for that. The next, we move onto the mixed autoregressive moving average model. It's just the combination of the two different types of model. The third one is the combination of the two models we have just written, and it is called the mixed autoregressive moving average model. So for more on this topic, you need to subscribe to this channel. So it is called the mixed autoregressive moving average model. The mixed autoregressive moving average model is denoted as ARMA of order PQ. Of order PQ. The autoregressive moving average model, sorry, the autoregressive model is of order P, while the moving average model is of order Q. So we can write the model itself. So it's defined is defined as the adventures phi plus, we now put down that of the autoregressive, we say summation of as I running from 1 to p, if you can remember, phi p or phi I, then x t minus p plus, because it is combined. This is for the autoregressive. Now we have summation of j running from 1 to q, theta k x t minus q plus et. plus E2. So this is what we get if we want to write the model for the autoregressive moving average. So the AMA model of order PQ is this. Now, we have to write the general form so that we see how we can use this model. So we say the general form, we write it this other side of the board. So we have to clean this part to write the general form of this model. For more on this topic, you need to subscribe to this channel. So we have to put down the general form. The general form of the model can be written as xt to be equal to, this is our constant, plus, we say phi1 xt minus 1 plus, it continues to give us summation of as I running from 1 to p, then phi p xt minus p plus, it continues, we now have theta 1 x p minus 1 for the moving average plus, it continues like that to give us summation of as j running from 1 to q theta p x p minus p plus et. So this is the general form of this model. If you want that, the autoregressive here comes first, while the moving average of order Q comes second. That is how it is here. The autoregressive came first, and the moving average came second. So what we just finished writing is the autoregressive moving average model of order PP. So it's a mixed model. It's mixed. Now, we can be asked to write AMA 2, 3. That means autoregressive moving average model of order 2, 3. We can do that. So we can do that. Okay. If we are asked to write ARMA of order 2, 3 model, we can be asked to write this model. What do we do? Very simple. We say ST is equal to autoregressive before we put first. Autoregressive. So we write lambda, which is our mean. Sorry. We have to define the parameters first. Let's define the parameters before we take that. Let's define the parameters. Now, the xt is our time series values. We have our phi1 to phi p, which is parameter coefficient. Parameter coefficient for AR, that is autoregressive model. For AR model, also theta 1 to theta q are still the parameter coefficient for NA, the moving average model. We also have this ET. ET is the white noise, or you call it our error term. Error term, and lambda is the constant. Lambda is the constant. So we just take some examples to show how it is written, how the AMA model is written. For me to do that, we move over to this side of the board to show that. For more on this topic, you need to subscribe to this channel. Now, how can we compute the AMA model? For example, if we are given compute the AMA model of order 2, 3. So what this simply means is that we have the autoregressive model of order 2 and the moving average model of order 3. So this is what we have. Now, how do we write it? First, our XP is equal to, we can write first the autoregressive model, which is phi 1 XP minus 1 plus phi 2 XP minus 2, which is this, the autoregressive, plus the continuous, plus right summation of as I running from 1 to p, phi p x p minus p plus lambda plus, we continue with the moving average. The moving average will have theta 1 x p minus 1 plus theta 2 x p minus 2 plus theta 3 x p minus 3 plus it continues like that to give us summation of j running from 1 to q theta q, then x p minus q. So this is how we can compute the AMA model. This is how we can compute the AMA model. But now, since this continues, see what we do. We now have to delete this part. Sorry. Since it's a combined model, see what we do. We have to delete that part. We just write lambda plus theta 1 x p minus 1 plus theta 2 x p minus 2 plus theta 3 x p minus 3 plus et. You are still correct. You are still correct. So this is how we write it. We can also be asked to write the AMA model of order, this time 3 here, and this time let's say 2 here, model. So what this simply means is that we have the autoregressive model of order 3, and we have the moving average model of order 2. So we can still write it out. It will give us Fp is equal to phi 1 xt minus 1 plus phi 2 xt minus 2 plus phi 3 xt minus 3. This is because we have it of order 3. That is why we stop at 3 plus our constant, our constant term. Then we now continue with the moving average part. The moving average will now be theta 1 xt minus 1 this side, theta 2 xt minus 2. We have it of order 2, then plus our error thing. So this is how the auto-regressive moving average model can be computed. This is how it can be computed in time series analysis. So for more on this topic, you need to subscribe to this channel to get more on what we have been doing.